Picture a Laurent series, an infinite sum of terms, some with positive powers of z minus z naught and some with negative powers. Somewhere in that sum sits one special term, the coefficient attached to z minus z naught to the power of -1. That one coefficient has a name, the residue. Pattern to recognize: out of an entire infinite Laurent series, only one single coefficient matters for everything that follows, the one attached to the power of -1. Here's the remarkable fact: if you integrate a Laurent series around a closed loop term by term, almost every term vanishes completely. Only the -1 power term survives, no matter what curve you integrate around. Pattern to recognize closed loop integral of a Laurent series: everything cancels except the residue term. Because only the residue survives, we get an extraordinary shortcut, called the Residue Theorem. If a closed curve C encloses several singularities, then the closed loop integral over C of f of z dz equals 2πi times the sum of all the residues trapped inside. Pattern to recognize: whenever you see a closed loop integral around multiple singularities, stop trying to integrate directly. Find the residues instead, add them up, and multiply by 2πi. Worked example 1. 3 poles, 3 residues. The function is f of z equals 1 divided by z times z minus 3i times the quantity z plus 1 squared. This gives poles at z equals 0, at z equals 3i, and at z equals -1, where the pole at -1 is repeated, so it's order 2. Finding the residue at the simple pole, z equals 0. Step 1. Factor out the piece causing the singularity, the 1 divided by z part. Step 2. What remains is analytic at z equals 0. Step 3. Evaluate that remaining piece at z equals 0. 1 divided by the quantity 0 minus 3i times the quantity 0 plus 1 squared, which equals 1 divided by -3i, which simplifies to I divided by 3. Finding the residue at the simple pole, z equals 3i. Same method. Factor out the singular piece, then evaluate what remains at z equals 3i. Working through, the quantity 3i plus 1 squared equals -8 plus 6i, so we get 1 divided by 3i times the quantity -8 plus 6i, which is 1 divided by -18 minus 24i. Rationalizing this fraction gives -3 plus 4i, all divided by 150. Finding the residue at the repeated pole, z equals -1. Pattern to recognize: repeated poles need one extra step, differentiate first, then take the limit. Step 1. Multiply the function by the quantity z plus 1 squared to clear the singularity. Step 2. Differentiate the result once, giving negative the quantity 2z minus 3i divided by z squared times the quantity z minus 3i squared. Step 3. Take the limit as z approaches -1. This gives the quantity 2 plus 3i divided by the quantity -1 minus 3i squared, which equals the quantity 2 plus 3i divided by the quantity -8 plus 6i. Rationalizing gives 1 minus 18i, all divided by 50. The general shortcut formulas, memorize these. For a simple pole, order 1, multiply the function by z minus z naught and take the limit as z approaches z naught. For a pole of order 2, multiply by the quantity z minus z naught squared, differentiate once, then take the limit. For a pole of order k in general, multiply by the quantity z minus z naught to the power k, differentiate k minus 1 times, divide by the quantity k minus 1 factorial, then take the limit. Pattern to recognize: the order of the pole tells you exactly how many times to differentiate before taking the limit. Order 1 needs 0 derivatives, order 2 needs 1 derivative, and so on. Worked example 2, 2 simple poles with a trig function on top. The function is sin of z divided by the quantity z minus, the quantity 2 plus I times the quantity z minus, the quantity 3 plus 2i. Both poles are simple since the denominator has 2 distinct linear factors. For each pole, multiply by the matching factor, cancel it, then plug the pole's value directly into what remains. The residue at 2 plus I is sin of the quantity 2 plus I divided by the quantity negative 1 minus I. The residue at 3 plus 2I is sin of the quantity 3 plus 2I divided by the quantity 1 plus I. Pattern to recognize: whenever a function is a ratio of two polynomials with distinct roots on the bottom, each pole is automatically simple, no need to check further. A useful theorem for spotting pole order from zeros: if a function equals one function divided by another, and the denominator has a zero of order m at a point, while the numerator doesn't vanish there, then the pole's order is exactly m. Pattern to recognize. Just check how many times the denominator's zero repeats. You don't need to expand anything. Worked example 3. Poles of a trig denominator function. The function is the quantity 3z plus 2 divided by sine of z. The poles occur wherever sine of z equals 0. These are z equals k times pi for any integer k. Checking the derivative of sin z at these points, cosine of k times pi equals negative 1 to the power k, which is never 0. This confirms every one of these poles is simple. For each pole, use the simple pole shortcut. Substitute a small shift, w equals z minus pi, and use the identity sine of the quantity w plus pi equals negative sine of w. This turns the tricky limit into the standard limit, w divided by sine of w, which always equals 1. Working this through, the residue at z equals pi comes out to negative, the quantity 3 pi plus 2. Pattern to recognize: whenever a limit gets stuck on a trig function near a singularity, try shifting to a small local variable. This usually reveals the standard w divided by sine of w shortcut hiding underneath. The general formula, verified numerically for k equals 1 and k equals 2, is the residue at z equals k pi equals negative 1 to the power k times the quantity 3k pi plus 2. Watch the sign carefully. It flips with every integer k. Worked example 4. A contour integral using hyperbolic functions. We want the closed loop integral over c of z times hyperbolic tangent of 2 pi z dz, where c is a circle of radius 1, centered at 2i. Step 1. Rewrite hyperbolic tangent of 2 pi z as hyperbolic sine of 2 pi z divided by hyperbolic cosine of 2 pi z. Step 2. Find where the denominator vanishes. These become the poles located at the quantity 2k plus 1 times I divided by 4 for any integer k. Step 3. Check which of these poles actually sit inside the given circle. Only poles trapped inside the contour matter. Checking the distance from the center, 2i to each candidate, 4 poles land inside this particular circle. 5i divided by 4, 7i divided by 4, 9i divided by 4, and 11i divided by 4. Step 4. Confirm each trapped pole is simple. Step 5. Apply the shortcut. For this particular function, the residue at any simple pole, z0 of hyperbolic tangent of 2 pi z, simplifies neatly to z0 divided by 2 pi. So the 4 residues are 5i, 7i, 9i, and 11i, each divided by 8 pi. Step 6. Add the residues together and multiply by 2 pi I. The 4 residues sum to 4i divided by pi. Multiplying by 2 pi I gives 2 pi I times 4i divided by pi, which equals 8 pi times I squared, divided by pi equals negative 8. So the final answer is negative 8. Sometimes a completely real-valued integral over an angle theta from 0 to 2 pi can be secretly reinterpreted as a walk around the unit circle in the complex plane. Pattern to recognize: whenever you see an integral involving cosine theta and sine theta over a full 0 to 2 pi range, consider substituting z equals e to the I theta. Step 1. Replace cosine theta with the quantity z plus 1 divided by z, all divided by 2, and sine theta with the quantity z minus 1 divided by z, all divided by 2i. Step 2. Replace d theta with dz divided by iz. Step 3. The entire integral becomes a closed-loop integral around the unit circle, now solvable using residues. Worked example 5. A real trig integral via residues will show that the integral from 0 to 2 pi of 1 divided by the quantity 3 minus cosine theta d theta equals pi divided by the square root of 2. Step 1. Substitute z equals e to the I theta. Step 2. Simplify the resulting expression into a ratio of polynomials in z. The integral becomes the closed-loop integral of 2 divided by I times the quantity 6z minus z squared minus 1 dz around the unit circle. Step 3. Factor the denominator to locate the poles. Solving z squared minus 6z plus 1 equals 0 gives roots at z equals 3 plus or minus 2 times the square root of 2. Step 4. Check which pole lies inside the unit circle. Only 3 minus 2 root 2, approximately 0.172, is inside. Step 5. Find the residue there. It works out to 1 divided by 2 root 2 times I. Step 6. Multiply by 2 pi I for the final answer. 2 pi I times 1 divided by 2 root 2i equals pi divided by the square root of 2. Now let's extend this to improper integrals over the whole real line. Picture a giant semicircle sitting on top of the real number line, with its flat edge running along the x-axis, and its curved edge arching up through the complex plane. Pattern to recognize: as the semicircle's radius grows without bound, the straight bottom edge becomes the entire real line integral you actually want, while the curved top arc's contribution often shrinks away to 0, which we show using the ML inequality. Applying the residue theorem to the whole closed semicircle and subtracting off the vanishing arc leaves just the real line integral, equal to 2 pi I, times the sum of the residues in the upper half plane. Worked example 6, a classic improper integral. We'll use residue calculus to show that the integral from negative infinity to infinity of 1 divided by the quantity x squared plus 4 dx equals pi divided by 2. Step 1. Identify the poles by solving z squared equals negative 4, giving two purely imaginary poles, z equals plus or minus 2i. Step 2. Only the pole in the upper half plane, z equals 2i, sits inside the semicircle as the radius grows. Step 3. Apply the simple pole shortcut. The residue is the limit as z approaches 2i of the quantity z minus 2i divided by the quantity z minus 2i times the quantity z plus 2i, which equals 1 divided by 4i. Step 4. Multiply by 2 pi I for the semicircle's total. 2 pi I times 1 divided by 4i equals pi divided by 2. Step 5. Bound the curved arc's contribution using the ML inequality. It's bounded by pi times r divided by the quantity r squared minus 4, which goes to 0 as r goes to infinity. Step 6. Conclude that the real line integral alone equals pi divided by 2, matching the numerical check exactly.